This short note is about the use of principal components analysis to analyze molecular dynamics simulations. Let's say you have two-dimensional data. This could be, for example, the height and the weight of students in a class. So most likely the data will look something like this. So you can represent the size of students in this class by this two-dimensional plot, or you can draw a single vector which is neither the y-axis nor the x-axis through all these points, along which most of the variation in the data occurs. This vector is called the eigenvector, and the variance of the data along this vector is related to an eigenvalue. The eigenvalue is a scalar quantity, the eigenvector is a vector. For more complex data, this may not be weight and height, it could be some other type of data. The data might look like this. And then you can have two eigenvectors. One would go in this direction, while the other would go in this direction. So this would be eigenvector 1, this would be eigenvector 2. So in the second case, we have not reduced the dimensionality of our data set, but in the first case, we have reduced the dimensionality of our data set. How do we calculate these eigenvalues and eigenvectors? Since we are working with simulations, we will talk about what is called a covariance matrix, and for this we need to know some matrix algebra. So by definition, the covariance matrix is defined in the following way. You have some vector x minus the average value of x multiplied by the same but now a transpose. So this is called a covariance matrix. So let's take a very simple case. If x is equal to x1, x2, x3, then my covariance matrix will look like x1 minus x bar, x1 bar, x2 minus the mean value of x2, x3 minus the mean value of x3, and then the same matrix but its transpose. x1 minus the mean value of x1, x2 minus the mean value of x2, and x3 minus the mean value of x3. So the first matrix is a 3 by 1 matrix, the second matrix is a 1 by 3 matrix, and if you multiply these two, you will get a covariance matrix which is a 3 by 3 matrix. So just to remind you of some simple matrix algebra, if you have two matrices x, y, z, you multiply this by the transpose of x, y, z, you will get a covariance or a symmetric matrix, a 3 by 3 matrix, where the first elements will be xx, xy, xz. So you multiply this by this, this by this, and this by this. The second row will have yx, yy, yz, and the third row will have zx, zy, and zz. Now all of these, each element is an inner product, so dot product or a scalar value. So xy is the same as yx. So what you will notice here is that this element, which is C1, 2, so first row and the second column, is the same as this element, which is C2, 1. Similarly, C3, 1 is the same as C1, 3. When this is the case, then such a matrix is called a symmetric matrix. So let us make this matrix for this particular case here. So if my covariance matrix is x1 minus x1 bar, x2 minus the mean value of x2, x3 minus the mean value of x3, multiplied by the same vector but its transpose, I'm sorry, let's rewrite that again a bit more carefully. x1 minus x1 bar, x2 minus x2 bar, x3 minus x3 bar. So if I multiply these two matrices, I will get a large 3 by 3 matrix which will look something like this. The first element will be x1 minus x1 bar multiplied by x1 minus x1 bar. The second element will be x1 minus x1 bar multiplied by x2 minus x2 bar. So this one multiplied by this, and the last element will be x1 minus x1 bar multiplied by x3 minus x3 bar, and so on and so forth. The diagonal elements will all be like this. They are multiplied by themselves. And this value here will be the same as this value here, while this value here will be the same as this value here. So this is a covariance matrix of a vector which has three components, x1, x2 and x3. When you are doing a simulation of a system of n particles, you will have 3n such positions. So each particle has an x, y and z, and my covariance matrix will then be a 3n by 3n matrix. This is a symmetric matrix, as I had showed you in this particular case here. When you have a symmetric matrix like this, you can extract the eigenvalues and the eigenvectors. Without going into the details, if C is my covariance matrix, then you can make an operation such as this. This is called an eigenvalue problem. W here is a matrix which contains all the eigenvectors, and if you multiply both sides by W inverse, then you get the eigenvalue matrix is equal to the inverse of the eigenvalue vector is equal to the inverse of the eigenvector matrix multiplied by the covariance matrix multiplied by the eigenvector matrix. So this contains all the eigenvalues, while W contains all the eigenvectors. So for each trajectory snapshot, you have a covariance matrix. And now you can extract the eigenvectors of your trajectory. So the first eigenvector, which will be the first element of W, will be the direction along which the atoms are moving the most or fluctuating the most. So the first eigenvector will also have the highest eigenvalue. The second eigenvector will have the second highest eigenvalue, and so on. It turns out that the first few eigenvectors, let's say the first 10 eigenvectors, will account for nearly 90% of the fluctuations of a protein. So if you want to extract the most important motions in your protein, the principal components analysis is a powerful technique to do this. And this is what you have done in class with the protein tutorial. Also, you can take each trajectory and project it upon individual eigenvectors. So let's say you have the first eigenvector EV1 and EV2. You take one trajectory snapshot and you project it upon this two-dimensional space. So what you get is a cloud of points. In some cases, you might get a second cloud of points. What this indicates is that there are two key protein conformations, at least along eigenvectors 1 and 2. So this was a short note about PCA, and if you have questions, we can